Unit 5, Day 10, and the notes should start on page 33 in your packet. So we are looking at sketching graphs of functions and their derivatives. So our central question is, can I use information from the first derivative and the second derivative presented in multiple representations to predict and explain the behavior of the function? So it's kind of like working backwards. So what we mean by multiple representations is that I could get information about the derivative and the second derivative in a graph or a table or a function. So that's the several representations. So let's first kind of review here what the first and the second derivative reveal. So the first derivative, f prime of function f, gives the slope of f at any x value, right? When I say derivative, you think slope. We're going all the way back to that comment. So we're talking about the tangent lines and what their slopes are. So we know that if the first derivative is positive or greater than 0, the slopes of f are positive. In other words, they're uphill. And that correlates back to the function by indicating that the function is increasing. Because if we have positive slope, that means we're going vertically upward in function value. Similarly, if the first derivative is less than 0, that means the slopes of the function are negative. So the tangent lines are negative, and that means the function is decreasing. The function is decreasing in its value. The second derivative, f double prime of function f, gives the rate of change of the slopes of the function at any x value. And that's what gives the function its concavity, its curvature. So this is a lot kind of to take in. Okay, the rate of change of the slopes. So let's kind of connect the dots here. We already know that slope is a rate of change, right? So we know that slope is the rate of change of the function. So the second derivative is the rate of the change of the slopes. In other words, it's the derivative of the first derivative. Okay, so this gives the rate of the change of the slopes is saying, like, is my line getting more vertical or is my line getting flatter and more horizontal? That's what it's looking at. So that if we have the derivative, we're looking at those values. Well, let me give this comment first to just kind of tie that in. So the second derivative, if the second derivative is positive, the slopes are increasing. So let's think about this. If the slopes are increasing, that means they're either going from negative to positive, or they're getting more positive. So that is correlating into the first derivative increasing, right? If I say slope, you think derivative. So when we say the slopes of f are increasing, we're saying that the first derivative is increasing. So it means that, let's just kind of start with something that has a positive slope. And if it's increasing, it's getting more positive. It's getting more vertical. And so if that's the case, then we have a concave up. We have something that looks like a cup that holds water. If the second derivative is negative, the slopes of the function are decreasing. They're getting. Let's start again with that. Let's start with saying we have a function that has a positive slope, and if the second derivative is negative, that means that slope is getting flatter. Okay, and so we think about that as concave down, something that tends to spill water. So the slopes of the function are decreasing, and again, slope means derivative. So the derivatives are decreasing, and so this is kind of tough to wrap our head around. But we'll look at a few examples, and hopefully we'll have a better feel for it after you take these notes. Okay, so here's and again, I'm going to go back to that essential question where we have multiple representations of the derivative and the second derivative. So in this situation, we have the graph of the first derivative. So we're looking at something graphically. And And we also know that the value of the function when x is equal to 0 is 0. So it's asking you to predict here which of the following could be the graph of the actual function. I know I've got some duplication here. I'm going to make this function bigger, so the c and the d are going to disappear here. So we can kind of look at this. So, okay, so let's take a look at what we know. We know that we're trying to predict the actual function. We do have some information about the actual function. We know that when x is equal to 0, the function value is 0. Well, that correlates to these points. And that is true for all of these answer options, so that doesn't help us rule out anything. So let's take a look at what we know about the derivative here. Okay, so we know from 1 to 2 here that the value of the derivative is up here in the first quadrant. That means that the derivative is greater than 0. The derivative is positive. And we know that if we have a positive derivative, we have an increasing function. So we're going back to those definitions. And so an increasing function means it's getting bigger in value. So when we look at this, and that's true because this is all positive from 1 to 2, we have to have an increasing function over this entire domain. So let's take a look at the domains from 1 to 2 for each one of these and see if the function is increasing. So this first function here looks like it increases and then it decreases. So this is out because it's got to be increasing over that entire domain from 0 to 2. This function looks like it's increasing and then it's decreasing, even though it's all positive, but it still has this decreasing part here. So this is out because this information about the derivative is telling us that it's always increasing. So when we look at C, we see that the function is increasing all the way throughout the domain. So C is a possibility. And when we look at D, we see that D is increasing over the entire domain. So D is a possibility. Okay, so this information allowed us to rule out at least half of the answer options. So now let's go ahead and try to find some information about the second derivative. Now, it doesn't really explicitly state that we have any information about the second derivative, but we know that the second derivative is when the slopes of the derivative are changing. So we can look at that characteristic right in this graph. So if we just look from 0 to 1 here, you can see that we have this information about the first derivative, but that also tells us something about the second derivative. We know that these values are increasing. It looks like the derivative values start at 0, and then at the end of the interval here at 1, we have some sort of maximum value of the derivative. So we know the derivative is increasing, which means the slopes of function f are increasing from 0 to 1. So let's take a look at that information in terms of these two options here. If we look at this from 0 to 1, we can see that this has a concave up profile. And we know that if the slope is increasing, then the second derivative is positive, or in other words, we're concave up. So this, we have a concavity, which is concave up. Let's take a look at this domain here. From 0 to 1, we have something that's concave down. So we know it can't be D because D's got the wrong concavity. And so we're definitely looking for this concave up here, which is from 0 to 1, we're looking for concave up, and that's definitely the case here for option C. So option C is the correct answer. I should have had that circled. But option C is the correct answer, and we can stick an X through option D. Okay, let's take a look at another representation here. In question 2, we have a table. And not only do we have tables, but we have this information about the first and the second derivative. Okay, and the tables are, we're being asked to pick out which table represents the function. So we know that the first derivative is positive, it's greater than 0. And we know the second derivative is negative, it's less than 0. So what does that tell us? Well, a positive first derivative says the function is increasing. And And a negative second derivative says the derivative is decreasing, which also means that we're concave down. And so we need to take a look at what this means in terms of tables. So the first thing to acknowledge on these tables is I've highlighted all the x values. And notice we go from -2 to 0 to 2 to 4 to 6. So we're counting by twos all the way through each table. So that's that we need to recognize. Sometimes they don't use consistent increments, which makes the analysis a little more difficult. But in this case, we have consistent increments. So that's nice. We can just compare how the function values change then. Okay, so let's talk about table B here. Let's talk about the first derivative here. When we say the first derivative means the function is increasing in value because the first derivative is positive. So when we look at table A, we see that our function value is increasing. So this is potentially an option. We look at table B here, we see we go from 8 to 6 to 11 to 9. So this is not increasing over the entire interval, like it claims here. These two things are true for all values of x. So table B can be ruled out. Table C is increasing throughout the entire interval, so this is potentially a good answer, and so is table D. So that allows us to at least eliminate one option. Now let's take a look at this information. Okay, so this information is saying the first derivative is decreasing, then the second derivative is negative. So with the second derivative being negative means we're concave down. So what does that mean in terms of tables? Well, concave down means that we have this profile that looks like, it would spill water, or I say it looks like a frown. And so if we look at the first derivative decreasing, what that means is that slope values of f are decreasing. Okay, in other words, we're looking at if the slope values of the function are decreasing, it means that f is not growing. F is increasing, but f is not growing as fast as we go through the table. So let's take a look at table A. We started at a function value of 0, then we're up 2, then we're up 3, then we're up 7, then we're up 3 again. So we're jumping at increasing rates, not decreasing rates, except for that last step. So that's out because we need to make sure that our values are not jumping up as much each time we go down. So let's take a look at C. We jump up 2, then we jump up 5, then we jump up 8, then we jump up 10. So we're jumping up more each time we go through the table. This is actually a good table for when the second derivative is positive. And we would have a bigger gain each time, and we'd have that concave up profile, which is not what we're looking for. So that's out. So it's got to be D. So let's just kind of confirm it. We start at -15, and we jump up 10 in value to -5. Then we jump up, 7? And then we jump up 4, and then we jump up 1. So we go from 10 to 7 to 4 to 1. So as we're going through this table, we're jumping up less and less and less, and that gets us our concave down, which is a negative second derivative. So the answer here is D. For the last example, we're going to look at an analytical example. And so when we look at an analytical example, most often the processes that if we're looking for describing the characteristics of the curve, so in this case, we want to know where the curve is both decreasing and concave down. When it comes to analytical solutions, it usually follows the procedure where you do the first derivative test and get all of your critical values and get that first derivative number line set up. And then you do your second, you find your points of inflection and concavity, so you do your second derivative number line process. And then you can answer, that gives you a ton of information. You can answer both these questions for sure. So, pause the video, and because we've done this before, we did this graphically on day 8 in question 1. We did a graphical application of this, but you've been through this process a few times. This might be a question where you could pause the video and work through the solution and just check your answer. So if you're tuning back in, I'm assuming you've attempted the solution on your own. So let's go through this. So we need the first derivative. So differentiating this gets us x squared plus 4x minus 12. And so, let's talk about what both decreasing and concave down mean first. Sorry about that, I kind of jumped the gun. Okay, so concave down is where the second derivative is less than 0. And decreasing is where the first derivative is less than 0. So we're looking at for both of those situations, which is why the first derivative and the second derivative number lines are so important to create. All right, so we want where both of those things are occurring at the same time. So that means where the graph is overlapping. So getting back to the derivative, here's the first derivative, x squared plus 4x minus 12, and that equals 0 because we're finding our critical points. And so we're going to follow that same process of here's the first derivative, it's polynomial, we're going to factor and solve this. So factoring gets us x minus 2 times x plus 6. And then setting each one of these equal to 0 gets us critical points at 2 and negative 6. So we're going to set up our number line. And then we're going to test on either side. Now I'm leaving a lot of the math out because we've been through this several times. So I'm going to test negative 7. I'm going to put it into here. Putting in a negative 7 here makes this negative. Putting a negative 7 here makes this negative. Negative times negative is a positive. And that's all you need to do, even on the AP test. This is why they don't grade the number lines, because they know there's a lot going on that is mental math. Okay, picking something between negative 6 and positive 2, let's take 0. Putting 0 in here gets us negative. Putting 0 in here gets us a positive. Negative times a positive is a negative. And then testing 3 out here gets us positive and positive, so this is positive. So that's the first derivative number line. Let's move on to the second derivative because that needs to be part of the solution. So this differentiating this gets us 2x plus 4, setting that equal to 0. No factoring needed, obviously. So we have 2x equals negative 4 and x equals negative 2. So setting up the second derivative number line, we know we have a possible point of inflection at negative 2. It's only a point of inflection for signs to switch. So let's go ahead and figure out our signs on either side. So let's go ahead and test negative 3. So I'm going to put negative 3 into here. And so we have negative 6 plus 4. I know that's a negative value. So this is concave down on this side of negative 2. And let's test something over here like 0. Put 0 in here. We get 4, which is positive. So we have concave up on this side. So we do have a point of inflection at negative 2. We're not being asked about that, but we do. So before we make this conclusion, let's just see what else this gets us. So like I mentioned a second ago, this should say F double prime. My bad. That should say F double prime. I have a typo there. That's a really bad typo. So what else does this get us? Well, the other information this gives us is that we definitely have a point of inflection because our second derivative goes from negative to positive. What does this get us? Well, at negative 6, we go from a positive slope to a negative slope. So this gets us a local maximum. And from at positive 2, we go from a negative slope to a positive slope. So this gets us a local minimum at negative 2 because of our derivative changes and values. So those are other pieces of information that those number lines give us. None of that information answers the question, but I just thought I'd throw it out there because this solution answers a lot of questions. That's why we really rely on this solution for analytical solutions over and over again. Okay, let's actually answer the question. So both decreasing and concave down. So in order to make that determination, I'm going to take this number line and redraw it here. So we're looking for negative first derivative, negative second derivative, and that is right in this region here. They both have to be negative. So it's right in that region, and that domain starts at -6 and goes to -2. So our conclusion, our justification is that the function is both decreasing and concave down on the interval from -6 to -2 because the first derivative is negative and the second derivative is negative. So there's our justification. Here's our answer. We reference the function, so there's no ambiguity. Just a quick note on the brackets here. Whether you use curvy or square brackets, they wouldn't dock you either way. The convention is to use square brackets, but like I said, usually that never gets you a docked point. Okay, so when we get back into the classroom, we will go over the takeaways from the notes and use our time for guided practice and gradual release.